Okay, so welcome back, and let me start from where I left off in the part A of this lecture. So, in this part, we are going to discuss more about the molecular basis of diffusion. The question is why at all is the phenomena of diffusion that we see when basically if there is a concentrated amount of particles they spread out. They spread out in different directions. So how does one understand that in terms of molecular motion? And for that, we discussed Brownian motion, and we'll come to this diffusion again, as you'll see towards the end. Uh, so we are going to discuss Brownian motion and what is the picture you should have in mind. What kind of system are we talking about? So Robert Brown, I think, saw in 1927, sorry, 1827. That's what they write in the books about. He saw some pollen grains under the microscope, and they were continuously moving around in the water. So I don't know what is the size of pollen grains, but let's assume, let's talk about Brownian particles, 1 micron sized particles, often called the colloid. Colloidal particles are particles suspended in a fluid. And they are, what Brown observed was there was incessant, endless motion. They were moving in random directions all the time and they never seemed to stop. And he always wondered that if there is a viscous drag of the fluid, a particle stops. But how come these particles are continuously moving? And they were moving essentially in all possible directions, random directions. It was not a directed motion in that it was not moving in a straight line, it was moving in all possible directions. And the simple question which we now know. There's work by Einstein in 1905. So in 1905, which is that famous year where he also had photoelectric effect and so on and so forth, and special theory of relativity. He also had a paper on Brownian motion. Okay. So there was Brownian motion, and then there was further work just after 1905. I think somewhere it is listed in this slides. But taking all that knowledge into account, which happened at the beginning of the previous century, 100 years ago, relatively, it is recent, right? It's the same time when basically people were discovering out quantum mechanics. So at the same time, there was a understanding of statistical mechanics and Brownian motion and so on and so forth. Uh, anyway, so that's the historical perspective, and today we know we understand better why a particle does random motion in a liquid. And the reason you might have come across already in school books is because this Brownian particle, 1 micron sized Brownian particle, BP, so referred it to as BP, Brownian particle. Yes, the notes are being bombarded from all directions by uh, fluid particles, fluid molecules, essentially. And that somehow leads to Brownian motion. Now, that's a qualitative picture, story which has been told. Let's understand this a bit better. So, you have a 1 micron size particle, 1 micron is 10 to the minus 6 meters. And what is the average size of the water molecules? It would be order of angstrom. It might be 1, 2, 3 angstroms. So I'm doing an order of magnitude calculation. Let's say 1 angstrom is the size of a water molecule, maybe 2. Really doesn't matter for the purpose of our discussion, right? So it is 10,000 times smaller. Let's 10,000 times smaller than the Brownian particle, and tons and tons of them are colliding or they are hitting at very high velocities to the BP, the Brownian particle. Just to get a sense of scale, angstrom and microns, these are difficult things to think about, at least if you are not used to it. On the other hand, we humans are of 1 meter long. I mean, so somebody will be whatever 1.5 meters or 2 meters. Again, it doesn't really matter. Just like I said, let the water molecule be of size of the magnitude of 1 angstrom. Similarly, humans are 1 meter. Now that's a length scale which typically students and normal humans are very easily able to visualize. So let's think that we scale up the water size of the water molecule. We multiply the size of the water molecule by 10 to the power 10. The 1 angstrom into 10 to the power 10 will give 1 meter. So let's assume each of the water molecules are of the size of 1 meter, the size of a human. Correspondingly, we multiply the size of this Brownian particle by 10 to the power 10 so that it's in the same range, it's in the same scale, right? So we basically want to have an understanding how much bigger is this micron size colloid as compared to the water molecule. So we are multiplying both the water molecule and the micron size colloid by 10 to the power 10. And if you multiply 1 micron by 10 to the power 10, you are going to get essentially 10 to the power 4 meters, which is something like a 10-kilometer radius or 10-kilometer asteroid, essentially. Right? So the volume is much bigger. Remember that, because the volume goes as uh, radius cube. Yeah. But in terms of dimensions, in terms of linear dimensions, you could think that a 1 meter human is going and hitting an asteroid whose radius is 10 kilometers, which is 10 to the power 4, 10,000 times bigger, and going and hitting it at a very high speed. Now, I don't want to convert speed also. What is the speed? What would be the speed? Just 1 second. Just to tell you, without converting, the velocity of water molecules is around 500 meters per second. That's a very high speed. That's a very high speed. Just to give you just an idea. So basically 10 meters per second is 36 kilometers per hour, right? So 100 kilometers per second is 360 kilometers per hour. So 500 meters per second is essentially 3000, so 360, 3600 kilometers per hour. That's a pretty high speed, right? How can you get this number? I mean, this is the order of magnitude. You can just put in half mv square. So equipartition theorem is all that I'm using. So the average kinetic energy of the water molecules. Remember, whatever be the interaction, kinetic energy, uh, equipartition theorem holds. So half mv square is suppose uh, the average kinetic energy of a water molecule, and that will be equal to 3 by 2 kBt. You have to put in the mass of a water molecule, which will be order of 10 to the power minus 27 kg. Kb is R, the gas constant by the Avogadro number, and T is the 300 Kelvin, right, in room temperature. You'll get something in the order of 500 meters per second. Now, if you want to convert this as well by multiplying into 10 to the power 10, you will get some ridiculously high number, which is bigger, which is higher than the speed of light, right? So we are not going to try to think how fast that the water molecules are moving, because you'll get this ridiculous number. I mean, we'll get a number. The number is not ridiculous. It's just higher than the speed of light. But suffice to say that the water molecules move at extremely high speeds and go and hit the colloidal particle. And I mean, so in terms of mass, if you now calculate the mass, this is actually 10 to the power 12 times more massive than the water molecule, right? Because volume into density and so on. So So that's what is happening. How many water molecules are hitting? Remember, water, we are talking about water, not gas. And the water molecules are densely packed. It's almost space filling inside the liquid. Yes, they are moving around, unlike a crystal. Crystal particles only vibrate about the minima of the potential. But here, water molecules are interchanging positions. They're moving around at high speeds, at that speed actually. So let's estimate how many water molecules are around the surface of the colloid. Right. So what is the surface of the colloid? 4 pi r square, where r is the radius of the Brownian particle, dt. And sorry, there's a whole square mid. Yeah. So that's the size of that's the surface area of a colloidal particle, 4 pi r square. And if you take that, basically there are a small water molecules sitting on the surface of the colloid, and there's a whole square missing here. You can estimate that the number of, consider the water molecules to be a small circle of size of area, again 4 pi r0 square, where r0 is the radius of a water molecule. Again, take it to 1 angstrom if the size is 2 angstrom. And you can immediately get that there are approximately 10 to the power 8 water molecules surrounding the surface of a colloidal particle. Now, these are liquids, and as I said, they are space filling. Uh, so, intermolecular distances are order of 5 angstrom, just as an ease of calculation. Doesn't matter if it's 4 or 3 or 6. And speed of water molecules is 500 meters per second. These are densely packed. Densely packed is important because every time it moves, it's going to go and hit another water molecule. So if you just divide, get an estimate of the collision time scales. There is each water molecule is colliding with each other or moving and colliding even with the colloidal surface once in 10 to the power minus 12 seconds, right? Remember, for gas, this calculation would be very different. Why would it be different? Because gas molecules are not densely packed. So when gas molecules are moving in any particular direction, they are not going to be, so if the gas molecules, whatever the density of gas molecules, they're not going to move an interparticle gas molecular distance and hit it, because much of it is free space. So you have to really calculate the mean free path. So for water molecules, interparticle distance is order of 5 angstroms. But for, I think, if I remember correctly, in your kinetic theory of gases, they will teach you the mean free path, and it is order of 50 nanometers, if I remember, or maybe more. But I think there are many more gas molecules. I mean, just like I estimated this 5 angstrom, the average interparticle distance as the sum of two diameter radii of for the water molecule. You can't do that for a gas. You have to be much more careful. You have to calculate the solid angle and so on and so forth, because every time it moves an interparticle distance, a gas molecule, it's not going to undergo a collision. Here, it's a relevant assumption, 5 angstrom. Uh, Point is also that numbers matter, right? You can't just simply extend whatever I'm saying for a liquid to a gas. That's all that I'm highlighting. But so there's an average of each particle is colliding with the Brownian particle 10 to the minus 12 seconds, right? And each particle is colliding. So there are around 10 to the power 8. Okay, maybe half of them, because are moving away from the colloidal particle and half of them are moving towards the colloidal particle. If not 10 to the power 8, okay, 1/4 into 10 to the power 8, or half into 10 to the power 8 collisions. every 10 to the minus 12 seconds. So then in 1 second, right, there are 10 to the power 8 particles. Okay, half of that into 10 to the power 12 collisions, or 10 to the power 20 collisions that are happening of the water molecules at very high speed in 1 second. So here this is a schematics, the large number of water molecules hitting in this direction and in this direction and in this direction and in this direction. And after drawing this, I realized that all the arrows look as if they are hitting the spherical surface normal to the surface. That need not be true. Just to correct so that you have the right picture, I've drawn these red arrows. There can be also bounce off, right? I mean, something can, are there pictures here of bouncing back? I think here there are these bounce back collisions. I have these, there can be angular collisions as well, but we are doing an order of magnitude estimate, right? So the point is, at every instant of time, the number of particles, fluid particles, hitting from this direction and hitting from this direction need not be equal. And similarly, the amount of, also the particles are moving with different speeds. And not all of them are hitting normally, they bounce back and so on and so forth. So from different directions, there might be a net momentum which this colloidal particle is getting due to the collisions with the fluid particles, right? Remember, this colloidal particle is, I think I calculated 10 to the power 12 times heavier than the fluid particle. But the fluid particles are also moving at very high speed. So small mass into high speed is a reasonable amount of momentum. What is the point? The point is there might be an imbalance in the number of collisions or amount of momentum transport. Momentum transfer from the fluid particles to the colloidal particle, right? It might move a very little. It might move a very small step. It will take a small random step of a random length in the plus x or the minus x direction in a small amount of time, where small amount is much smaller than 1 second, right? Because there are so many collisions happening per 10 to the minus 12 seconds. So it might take a small amount of time, a small amount of displacement of different length, random length. This word random could remind you of the random walk we were discussing previously. And there would be a small displacement in the x direction and a small displacement in the y direction and a small displacement in the z direction. Now, if you have your Newton's equation of motion, you can, in principle, if you can manage to handle 10 to the power 20 collisions and all the force fields, and you remember the water force fields are pretty complicated, they have high dipole moment, you can exactly calculate how much there's a displacement. But getting through these numbers, like 10 to the power 20 collisions in 1 second, and calculating that is meaningless. I mean, you might have the number, but that it is not going to give you any physical picture. After all, you're doing your measurements and looking at the position of the colloidal particle every 1 second, or maybe 0.1 second, or maybe 1/10, 1/20, 1/100th of a second, but not much smaller than that. The very fast cameras maybe take pictures every millisecond, but calculating so many collisions, having this huge amount of data is a useless exercise, even if you can do it, right? Rather, you want to capture what is the essence of the physics which is happening. What is happening? You don't want to know the gory detail in the position and do a huge data analysis to do that. Instead, what you want to know about is have a simple description of the emergent phenomena. So this word emergent, even if you know all the details of the calculation, you really don't want that. You want a simplistic, effective description of how the Brownian particle moves, which is much more simpler, which will give you a physical intuition. And that is where we want to head at. Instead of knowing all the detailed position of each of the particles and each of the Brownian particle, both the fluid particles and the Brownian particles. And yeah, and in so to move in this direction, basically, what I'm going to tell you now is a lot of derivations, calculations, realizations clumped or summarized in a half an hour lecture. So we'll discuss all of this. In 1905, Einstein actually also came up with the so-called Stokes-Einstein's equation, and that is at the end of this lecture. We should briefly mention it, the content of it, because Einstein also, it's at that time that Boltzmann had come up with this molecular theory of collisions of gas particles. And Einstein wanted to know, okay, why is there Brownian motion and so on and so forth. Statistical physics was coming up. Um, um, and, and in 1908, there was the Lajoie equation, which gave a very simplistic description of the motion of this Brownian particle, which we'll see soon. And believe it or not, that there are indeed molecules and atoms, I mean, it might have been postulated and hypothesized much earlier. I don't know, by Dalton and Boltzmann and so many. But you can hypothesize, you can theorize, whatever. You can theorize that I have four, I don't know, horns. But the proof, the real physics is in experiments, which we in India often forget to emphasize. And the actual proof that there is molecular motion and the presence of molecules, because there was an experiment done which basically embodied all the hypotheses of Boltzmann and Einstein and Lajoie, who assumed that there would be molecular collisions. I mean, these things which I told you, that there would be collisions. Brownian motion is a consequence of collisions. Of course, at that time they would not have known the size, the exact size, and they even didn't know what was the Avogadro number. They had an estimate for it, but the accurate value of Avogadro's number, KB, KB is R by Na. What is the value of Na? You can't find out KB unless you know Na. You might know the gas constant to great accuracy. And that was found in 1909 in Perrin's experiment. He not only found out the value of KB by figuring out the value of Na, his experiment also had put in, had the theory that he used already had the idea of molecular collisions. So in an indirect way, there was a proof that molecules exist. That was as late, I don't know, for you it might seem a century, but it's just the previous century. And now we take atoms for granted. You can take pictures of atoms in STM and so on and so forth. But that they really exist, what is the accurate value of Na, was figured out as late as 1909. And that gas molecules collide and all the stuff that you read in your BSc first year, second, third year, second year, Maxwell Boltzmann speed distribution. Yes, it was assuming molecules and assuming gases and assuming collisions, weak interaction, that was derived earlier by Boltzmann and so on and so forth. But who says that was true? It was experimentally proved as late as 1927. That's even after your Schrodinger's equation. You can look up the paper. It's a very beautiful experiment. Typically, we don't teach this in our, so we are always focusing on the theoretical derivations. But I mean, if we teach whatever has been accepted and validated experimentally, else one can theorize whatever they want, but they don't become the truth unless validated experimentally. So yeah, never mind. So that got validated as late as 1927. So that's again the belief. I mean, whatever was assumed in the collision of gases and so on and so forth, so that you get the Maxwell-Boltzmann speed distribution and RMS velocity, all of these, the values that they actually match, and the value of KB, all of these were rather recent, as recent as when quantum mechanics was developed. So that's the historical background, I think, is very important. What I also wanted to emphasize is the role of experiments. Without role of experiment validation, just a theory, just a hypothesis, right? Okay, with that background, coming back to the topic, so we were originally discussing that how does a Brownian motion move, and you might have qualitatively heard that moves due to the collision with the liquid molecules around the Brownian particle, the pollen grain. But let's have a more quantitative understanding, right? And this is typically taught either in StatMech 1 and StatMech 2, but I'm not going to do all the derivations, just tell you the physical content of it. So the description, so basically Lajwa wrote down the equation of motion m d2r dt2 is the Newton's equation, right? And but this is the Lajma equation because m d2r dt2 minus grad v being the potential, m d2r dt2 equal to force, the conservative force, is the so-called Newton's equation. But now you want to study the effect of a Brownian particle which is being bombarded by tons and tons and tons of fluid molecules. And if you want, and you want to incorporate the effect of these millions and billions of collisions, what effect it has on the motion. And you already know from experiments, Brown's experiments, that it is a random motion. So why are we writing down the equation? We are writing down the equation because we want to have a quantitative idea rather than just say, oh, it is moving in random directions. We want to have a quantitative idea. How much is it moving? In how much time? To have these ideas, we need an equation, and that equation again has to be verified by experiments to check whether the equation is correct or not, because we can come up with multiple equations, right? So what Lazarus proposed is m d2r dg2 equal to minus grad v, and the effect of the fluid collisions, the collisions of the fluid molecules with the Brownian particle, can be incorporated by a frictional force minus zeta v. Now this minus zeta v you have seen in the past when you have done an experiment of taking a sphere and dropping it in a huge tube of water. I think it's called the Stokes experiment. And it reaches terminal velocity. This is stuff of your school or college when you are in college. Um, then you say that if a sphere is accelerating in a tube, um, falling, then finally it will reach terminal velocity. Why will it reach terminal velocity? Because there's a force acting mg, right? It should decelerate. But there is also a frictional force which prevents, which is pointing in a direction opposite to that of mg. And when these two forces balance, you reach terminal velocity. It is that minus zeta v, frictional force into v. right? But that was studied for a massive particle. Here you have multiple collisions, and you know that the particle is moving randomly. So the effect of molecular collisions is taken care over and above the conservative force over the frictional force and a random force, Fr. Now note that I have given basically I have given a vector sign. This is a vector equation, but what you could also do is just write it in the x component d2x dt2. Then you take the x component of the force and the x component minus zeta vx, and then you would have a random number, right? Uh, so it's a vector equation, but you can write it down in x, y, and z. So you would have a different value of a random force, this is a force equation, right? All the terms have dimensions of force. And here also you will have a random kick, which is giving to the Brownian particle. Of course, when it was proposed, it was validated, and that's why I'm telling you that. I mean, this was a proposal, and then now we know that this is the truth because you'll figure out. Anyway, so each particle also feels a random kick. Now, going further, just to summarize, so what did we learn? So let's look at this. So basically, what I'm saying is by the Lagrange equation that if you are looking at the motion of a Brownian particle at large time scales, when I say large time scales, I don't mean hours or days. I mean 1 second, millisecond, 10⁻⁶ much larger, large with compared to what? Much larger than the molecular collisional time scales, which are 10⁻12 seconds. As long as you're looking at long time scales where there has been multiple rounds of collisions by each particle which is bombarding on the BP being the Brownian particle, the effect of multiple collisions of the BP with the molecular fluid particles can be replaced by the random motion of the colloid being the BP. So the Brownian particles are often referred to as colloids, and you can have spherical colloids, and you can have rod-like colloids, you can have arbitrarily shaped colloids, and so on and so forth. Any particle which is suspended in a fluid, we call it a colloid. And the stochastic dynamics, random dynamics, can be quantitatively described. Now, quantitatively is not the same as Newton's equation of motion, where you know where each particle is after a certain amount of time, if you know the force acting on it and the initial velocity, initial position. Here, the particles are moving randomly. So when you say that a position of a particle in a fluid bath can be quantitatively described, it means only in a statistical sense. What does it mean in a statistical sense? We will come to it. But we are saying that statistically, the motion of Brownian particles can be described by the Lagrange equation, where essentially over and above your standard Newton's equation, we have also incorporated effect of the force, the frictional force. This is a conservative force, a force which can be derived from a potential. This cannot be derived from a potential, and this is a random force. So the effect of collisions is not taken into account only by a random force. It's the combination of the noise term, the random force, and the viscous dissipation. The effect of the fluid is both, not just the random motion, random kick. Random kick balanced by the frictional force of zeta v. Both the terms together describe the effect of multiple collisions of the fluid particles with the colloidal particles. There are two terms which come in together, right? So the noise term is essentially, it gives kicks, random forces, random kicks in random directions, or if you like, you can decompose it in the x, y, and z direction, and it adds energy to the colloid. Right, you are giving a force to the colloid, its velocity would increase. So there is adds energy to the um colloid, and that's why it has to be balanced by the dissipative term. Energy is lost when the particle is moving. There's an equal and opposite, not opposite. There is a, sorry, not equal. There's a force opposing its motion through the fluid. It's dissipating energy. It slows down the motion. Its direction is minus zeta v. If the velocity of the colloid is in v, then the force acting is opposite to the direction of its velocity. Minus zeta v, it takes away energy from the Brownian particle. Right? Now, what do you see? So, one is adding energy, one is dissipating, taking away energy, slowing down the motion of the Brownian particle. Now, we know from Robert Brown's experiment that this particle keeps on moving endlessly. Pollen particles or Brownian particles move on endlessly. They don't stop. They move at an average. I mean, you can make it quantitative also. How much does the particle move around? What is the average displacement? But wait for that. So what you see is the same manner the particle goes on incessantly moving endlessly if you watch it today, tomorrow, and so on and so forth. So it's neither speeding up nor slowing down, which means that these two terms, the kicking and the dissipation force, have to be balanced. In some way, the energy lost is to be balanced by the energy gain, right? Else the system here, the particle under observation is the Brownian particle. So that's what I mean by the system. Of course, the system actually means the Brownian particle in a bath of fluid particles. Else it wouldn't do Brownian motion. If there was no fluid, you take a Brownian particle and kick it in space, it will move in a straight line. Move because it won't feel the collisions, right? If it moves, feels the collision of interstellar, whatever dust particles, it will be at a much larger length scale and so on. We are really talking of Brownian particle. We are focusing on the Brownian particle, but it's in a bath of fluid, right? It neither speeds up nor slows down, right? Sorry. So dissipation and noise have to be related to each other. They have to be balanced with each other, right? So, I mean, I hope I convinced that. And so this behavior, the statistics, so the question next to ask is, okay, we wrote down the Langevin equation, the Langevin equation is in French, but we haven't yet specified what is zeta. The zeta we specified is the same friction which you face when you drop a sphere in a tube of water. But what about the noise? They are related, but what is its strength? So let's specify that. So all this can be derived, but I'm just telling you the results so that you get the big picture. And you can go into the statistical physics book and get all of this information, right? So, so the statistics of this random force is at any instant in time t. Suppose a random force Fr is acting, and at any other time uh, t0, F dash R is acting, and you take the product, you multiply them, and take the time average, expectation value, time average if you like. Do it in a 1D, and you can similarly do it in a 3D. dot product if it's a 3D. Let's take a 1D case. Suppose you make multiply them and calculate the average. Now, when you are trying calculating this time average, you are calculating this time average at the millisecond or microsecond or 1 second range. You're taking a time average through which there have been multiple collisions, right? So you're not doing a time average of 10 to the minus 10 seconds or something. You're really taking a time average of milliseconds. And then you will see that if you because if you take it at 10 to the minus 11 seconds, they might be correlated. This noise might be correlated. But it's only when it has lost the memory, there has been multiple billion collisions, round of collisions, is this valid. So if you take the product, then this can be written as some constant, and that constant later turns out to be 2 zeta. Zeta is that frictional force constant, kBt. After all, this is a thermal-driven phenomena. The particles have speeds and velocities, the fluid particles, due to kBt, thermal energy, thermal bath, statistical physics. 2 zeta kBt delta T minus T0. Where does this delta T minus T0 come? So this means that if you take two forces at two different instances in time and multiply it, this could be positive. It is being kicked in the positive direction. At a different instant in time, that force might be the negative direction. But you're multiplying all such pairs and taking a time average, then it is equal to 0 if t is not equal to t0. It is delta correlated. On the other hand, if t is equal to t0, then whatever force be it, whether it acts in the positive direction or negative direction, large force, small force, uh, whatever be it, yeah. So this force is a Gaussian random noise. It's a Gaussian random noise, and if you take the whole square of it, which is at the same time, take the square of it. So whatever be the sign, whole square is a positive quantity, and then take the time average, its value comes out to be 2 zeta kBt. Zeta, friction constant. 6 pi eta r. You have seen this. I mean, this 6 pi eta r actually holds only for a spherical particle, and if it is much larger than the molecular dimensions. Why did I say this? I really don't want to dwell upon it. But if you have a massive particle, massive micron-sized particle is considered massive with respect to the fluid particle. In that case, one can assume continuum fluid mechanics and stick boundary conditions, basically the fluid velocity on the surface of the colloid is the same, I mean, as the colloidal surface, velocity of the colloidal surface is that stick boundary condition. And only if these conditions, and that would hold true if the spherical particle is much larger than the molecular dimensions, then this friction constant, and your massive sphere which you drop in a column of liquid is obviously order of 2-3 millimeters, 5 millimeters. So that's a massive particle compared to that of molecular dimensions. And then 6 pi eta r holds. That's the friction constant. But what do you observe? You observe, first of all, that this noise, this random force, random kick, what is the magnitude of the kick? It's random. But this noise, the distribution of these forces has a certain distribution, statistical distribution. It's a Gaussian random noise with the variance being 2 zeta kBt. Right. So basically, if you take a distribution of f, how large is f? How small is f? What is the probability that you're going to have a large f? What is the probability you're going to have a small f? Large, small with respect to what? The standard deviation. And inside that, you see KBT is sitting there. Thermal fluctuation, thermal energy is sitting there. Right? Uh, so, so that is going to be your essentially distribution. I mean, that's what the variance of the distribution is. And then within that, you are going to have a large number of small forces. Why? Because Gaussian is peaked near the middle, near zero. We are going to have large number of small forces and a few very large forces. Large with respect to what? With respect to the standard deviation, or rather square root of this is the standard deviation, right? So that gives you the distribution of forces with which a particle is being peaked at large time scales, much larger than the molecular dimensions, right? Uh, as a consequence of which, the particle is going to do a random motion, right? Note zeta is sitting there, so that's so inside zeta. Now note what is there inside zeta. You have the viscosity of the fluid. What is the viscosity of the fluid? It's a fluid property. On the other hand, r is the radius of the colloid. So inside the friction coefficient, both a fluid property and a property of the radius of the colloid is sitting inside, and the frictional random force. So this determines how much frictional force it feels. Of course, this into velocity, right? Now, if there is more R, more frictional force. There's more frictional force. The amplitude of these thermal fluctuations, because more number of particles are going to go and kick the colloidal particle. And hence you see the amplitude of the frictional random force has zeta, but it also has kBt. If you increase the temperature, the average velocity of the fluid particles is going to increase. It is going to go and hit the colloidal particle with a higher speed. Of course, all of them are going to hit the colloidal particle at a higher speed. Consequences, frictional force increases. Right? I mean, this the random noise, the random force, the magnitude of the random noise also increases. Of course, it's distributed. When I say the amplitude increases, I don't mean that at each instant it's larger. There are small force and large forces. It's Gaussian distributed. What I mean is that the standard deviation variance of this force increases, right? On an average, it feels a higher, on an average, a higher kick, depending upon a higher value of zeta and a higher value of kBt. The message is that the amplitude of the random force is related to the viscous dissipation decided by zeta and kBt. And moreover, they are delta correlated in time, right? Because at different times, the force could be in different directions. When you average over it, the product go to zero. But at the same instant in time, you basically square it, so it's a positive number, and then you calculate its mean magnitude, and that will be a positive number. Right? Higher temperature, Fr is larger, thermal kicks. I have already discussed all of that. Note that the equation, and yeah, so the point is also that the system is in thermal equilibrium with the fluid bath. Now, note the equation of motion m d2r dt2 equal to minus grad v minus zeta v plus, I mean, this is the so-called Lagrange equation. Now, you might, so if you want to, so in terms of one dimension, you can, instead of r vector, you can write x, the x component of the force, zeta dx dt, one random number generated, one value in one direction, right? And note here, previously we had a Brownian particle in a fluid path. Here the equation of motion is written only for the Brownian particle. The effect of the fluid particles are not, you don't have equation of motion for the fluid particle. The effect of the fluid particles and their collisions and momentum exchange and collisions and so on and so forth are all subsumed in these two terms, minus zeta dx dt plus f. So that is the message. All the Bach degrees of freedom are accounted for by this effective description. You have swept away millions and billions of equations of motion. You have an emergent effective, the effect of millions and billions of collisions are written down in terms of a simple stochastic differential equations. You see how simplifying it is. That is the beauty of physics, right? You don't need to know all the degrees of freedom or how each of them are moving. You come up with an effective, beautiful one equation which works, right? So let's go a bit ahead compared to what we had done before. Remember that this colloidal particle is in thermal equilibrium with the bath. So KBT is there. It is, I mean, those who have done statistical physics 1 or 2, they might relate to this thermal bath or the bath which keeps the system in equilibrium. So if you look at the average wake square of the colloidal particle, only BP, effect of all other things have subsumed in this effective description which describes statistically the dynamics of the Brownian particle. Dx square will be equal to kBt by m. Maybe there's a half missing. I mean, yeah, I mean, order of magnitude. If it's Vx square, I think there has to be a half kBt. Yes, half m. Oh no, half mv square equal to half kBt. So I have cancelled half from both sides. So Vx square equal to kBt by m. Note, when I have the expectation value, the time is well above the Smoluchowski time. Now that's a new term. I'll explain, though not derived. All derivations, pages and pages of it are there in the books. It will take 15 days or I don't know, 2-3 weeks class to teach all of this, maybe more. Uh, but I'm trying to give you the ideas and trying to correlate them without the derivations. Now, m by zeta has dimensions of time, and I'll tell you what Smoluchowski time is. So, if you looked at time, which is less than m by zeta, zeta 6 pi eta r, m, mass of the colloid, then you will see that the velocity is correlated. You will see that, okay, the particle is moving in the same direction for some time and then slowly it is changing direction. So the velocity is correlated below m by zeta time. It's only if you look well above this time scale, and this can be derived, will you see this random motion which I talked about? It's moving in one direction and another direction and so on. So only if the time of observation is higher than m by 6 pi eta r are you going to see this random motion. Before that also you will see the random motion, except that you will see velocity of the colloidal particle is correlated. If you go to even smaller times, right, even the noise will be correlated because, I mean, if you're looking at 10 to the minus 10 or 10 to the minus 11 seconds, it is going to have a memory that, oh, I got so many momentum transfer from, I don't know, half a billion freight particles. It's going to have memory. Noise is going to be correlated even at that time scale. But only if when you're averaging and looking at large, and I've already defined what is large, are you going to see this behavior? I mean, are all these equalities going to behave nicely? Else you need the details. There will be noise correlation. There will be velocity correlation. Just to give you an idea why m by zeta is a dimension of time. So this is a dimensional analysis. Force equal to zeta v, right? So force This is a dimension analysis, has the dimensions of ml t square. And velocity, I mean, this is force equal to zeta v. I'm not writing the minus here. V has dimensions of L by T. You can immediately get that zeta has dimensions of M by T and T has dimensions of M by zeta. Yeah. So M by zeta will give a certain time scale. Below this time scale, it will have its memory of the velocity correlation. So the way you calculate correlation is velocity at time t into velocity at time 0, expectation average. Only if t, when you are calculating this, is greater than m by zeta, will you see completely uncorrelated. Yeah. So above that time scale, essentially, what you see is that the motion of the Brownian particle, it is random directions. It's a random size step in plus x plus y plus minus z direction. That's so reminiscent of a random walk, right? It's like a random walk in 3D. Except when we discussed random walk, all the steps were of equal size. But then we discussed central limit theorem. And even if the if the size of the steps are of different sizes, Gaussian distributed maybe, they're not of equal sizes, but from a certain distribution, then a sum of random numbers, a large number of small, random steps will again be a Gaussian. Sum of many small random steps, even if they're not uniform, that again will be an Gaussian. And a question for you to ponder about is what is going to be the size of the step? If you want to map it from a random walk to this random motion of a Brownian particle, right? Brownian particle, which is moving around in different directions, random uncorrelated directions, of different amplitude, because that is going to depend upon the kick, the force, the random force that it is getting. How will you map this? What will be the average size? Well, I have not discussed that. You have to read a bit more. Not everything needs to be figured out in one lecture. Right? These are questions you can ponder about or take some time to think about over 1 or 2 months. Okay. So what are the questions? The questions is what is the size of the step, mean size of the step, because it is going to take different steps, of course, because the force is going to be different. The instantaneous random noise quick force is going to be different. And the question is how much does the particle move in n steps? Suppose each step is of time dt. Previously, we didn't talk about the time step. We just said increasing in time. Random walker was taking a step at a time. And at different times, suppose each step took time delta t. And it took n steps. How much does the particle move? That's exactly what we started out with the random walk discussion, right? We are coming back to that. But in this case, though the problem is sounds very similar, let's think about in 1D. Let's step in plus minus x or plus minus y or plus minus z. So what you basically want to ask is if it took n steps, so n delta t is some time, let's say ta, okay? And you want to know what is the mean displacement. Now, if there is a random walk, if this is diffusing and it is getting random kicks, forces, which some of it is in the positive direction and some of it is in the negative direction, and you take 1,000 Brownian particles and average, and some particles are going to go. So you're taking a time average and a particle average. So some are moving to the left and some are moving to the right. If you take a very good ensemble average, after a time ta, say, ta has n steps, say, right? Then the mean you will get 0. Average, some particles are moved to the right, some particles are moved to the left in absence of any external field. So the better quantity, just like previously, to look at uh, is delta x square. So basically you have some steps, large steps and small steps and large steps and large steps and small steps. And after n steps, you ask, what is the displacement after time ta? Minus x0. Suppose it started out at time t0. What was its position? Subtract the two, that is the displacement, whole square, and average. Yeah. You can average over time. You can average also and do an ensemble average. Why can you do it average over time? Suppose this was your origin. And from here, you calculate n steps. Okay, time ta. Let's say time ta is 1000 seconds, right? So you can start ticking at time t0. And after 1000 seconds, you measure what is your displacement. But what you could also say, if you keep on observing, right, that I'm going to observe, so I'm going to set how I'm also going to look at the displacement from 2000 to 1000 or 3000 to 2000. That again will give a delta t, n steps on an average, a ta minus 0. I mean, okay, so then it will be t 3000 minus t, sorry, x at t equal to 2000. You can also do as in that sense a time average and also a particle average, ensemble average of 1000 particles. You can take a different TB. So suppose instead of n steps, you look at 2n steps, right? 2n steps. Instead of 1000 seconds, you look at 2000 seconds. And you want to see how does this, so this is called mean square displacement. This is displacement square and then take the mean. Mean square displacement, MSD for short. So see xn t minus xn0. This is from some paper. I just randomly downloaded it from so that you can see a like, picture. So this is MSD, mean square displacement, versus delta t, Ta minus T0, Tb minus T0. Now, if Ta minus T0 might be 1000 seconds or whatever, milliseconds, doesn't matter. And this could be 10 to the power 4 seconds more. So basically what you are looking at is how does this quantity MSD change with choice of n. Remember, even previously I said all those random walk and all these things happen at large n. Now here you are starting at short t and going towards large t. So you want to see the entire effect. So at small times, what you see is that this MSD whole square goes as t square because it still has the ballistic effect. It is still moving in the same direction. It's not become the random force of Langevin equation, right? The random displacement. That random walk happens only at relatively long times. So you can figure out when MSD, mean square displacement, changes as t, right? It is here that it is going random motion, diffusive motion, random walk motion. Here it is correlated motion. So you basically look at the time where this t square exponent, where does t square come from? X equal to Vt. Right? Delta x equal to V delta t. Delta x whole square equal to V square delta t whole square. So When you have this displacement square, it is going as delta t whole square. It has the correlated motion. It has memory. It's only at long times that you get the so-called random motion reminiscent of a random walk where displacement whole square average was going as n being the number of steps, or here n delta t is the time. So displacement square square displacement is going at t only here. Here is where you get your random motion well above this Smoluchowski and other whatever Fokker-Planck. Never mind. Here it shows t to the power half and t to the power 1/4. Ignore it for the moment. These are more complicated effects. Maybe there is the Brownian motion moving in a mesh, some other microscopic biological mesh of proteins or whatever, dense system, that you can get subdiffusive motion. So these days, people typically, I mean, this is the standard textbook knowledge, right? What I'm telling you is 100 years old, textbook knowledge. That is what you will read in your, whatever, third year, fourth year Stat Mech 2 course. But this is the stuff of research. So I'm downloaded this from a research paper, right? So yeah, so when you look at chromosome dynamics, you're going to see all sorts of, or look at polymer dynamics, you're going to see such exponents. But what I'm telling you right now is the standard 100 years old textbook stuff. So whatever you are studying in your MSc, right, it's just textbook stuff. It's there in the books. It's 40, 50 years old. Whatever is new is not there in the textbook because people are still debating about it. So I'm talking about this stage, right, where you have the diffusive motion, right? Uh, okay, so it's taking quite some time, but what we are saying is delta x whole square. Okay, yeah. So once you get such a graph, once you have a behavior of how mean square displacement changes as time, you can take this part, you can first identify. So note this also, the point is this is a log graph. So if you plot it, this is well averaged and plotted in the log scale. So basically MSD, and only then you will get MSD goes as T here, this part. And once you have identified this part, now if you divide delta x whole square average is the MSD divided by the time. Here you were looking at different times. So basically, displacement squared divided by delta t. Suppose you calculated delta t here. 6 delta t gives you the diffusion constant, except now you have calculated the diffusion constant from microscopic quantities. So in the diffusive regime, delta x whole square goes as 6 n delta t or 6 dt, right? So sorry, here I think in this convention I should use the time here, not the delta. 6t. So delta x square equal to 6d. And here you are calculating d from the microscopic. So you can observe a Brownian particle, calculate how much displacement it has had, calculate the expectation value, look how much displacement square average over, let's say, 50 seconds, divide by it, you'll get your diffusion constant again. So this diffusion constant microscopic is equal to that macroscopic diffusion constant which we had discussed in diffusion equation when there was this del. You remember there was this partial differential equation, first order in time, second order in space. That was also diffusion constant. Now you have got a microscopic definition of the diffusion constant, and that is equal to kBt by zeta. Now that's the so-called Stokes-Einstein relation, which Einstein wrote down in 1905, and we'll have a cheap derivation of it in the next slide. So you will find that both the macroscopic diffusion constant, microscopic, they're equal because the origin is the same. See, when there is a concentration gradient, then each particle is doing a Brownian motion. It is moving in random directions, right? But, but, let's go back to that figure, this one. Each particle is doing a Brownian motion. This guy has equal probability to go to the left or to the right. But here, right, here there's a boundary. So on an average, a larger number of particles are moving from right to left compared to the number of particles which are moving from left to right. So the reason that the equilibrium, so basically you get uniform density at very long times, because this is high density, the number of particles which have moved from right, left to right is smaller than the number of particles which have moved from left to right. Even if these were infinite, even if it was infinite, here there is a higher concentration. So more number of particles are moving to left to right. If this was infinite, there would be a larger number of particles moving to the left as well. And again, concentration would become uniform. And here we had said, okay, the current, the number of particles is proportional to the concentration gradient, and thereby defined a diffusion constant. Here, in the Brownian motion, we are starting from a completely different direction. We are saying, okay, we are observing a Brownian particle, we are observing each of those particles, looking at how much displacement it has had in a fixed amount of time, taking an average, from there calculating the diffusion constant. And this is again the diffusion constant calculated microscopically. And previously we had the macroscopic, and of course they have to be equal because the two phenomena are related. The reason the concentration gradient becomes uniform are these molecular collisions, is the Brownian motion. And this diffusion constant, even if you don't do, even if you don't uh, know the diffusion constant, it is actually equal to kBt by zeta, friction constant. It's if somehow you can figure out the friction constant, somehow you know the radius of a particle, then you know its diffusion constant. Actually, this kind of relationship, if you know the radius of the particle, what is its diffusion constant, and does it really diffuse that much, and so on and so forth, is what is done by the theorist. What does the experimentalist do? The Brownian particle, they don't have access to the radius. They actually measure the diffusion constant, they actually measure delta x square, calculate the average, divided by the time. Here the delta should not be there. Hence they get the diffusion constant. Once they know the diffusion constant, and since they know that this relationship holds, kBt by 6 pi eta r, what is difficult for them? They don't know the radius of the particle that they are observing. They might calculate d, they know kBt, eta, they know the viscosity of the fluid. They estimate the radius of the particle by doing such measurements. And this is what is used in so many things. I mean, how do you know the size of a protein and so on and so forth? They use, I mean, they do something more. But what is going on is this Stokes-Einstein relationship, zeta, 6 pi eta r. The theorist will say, okay, I have a particle size of such and such, the fluid viscosity is such and such, it should have a diffusion constant of such and such, right? And then you match with experiments. Where experiments, they do exactly the opposite. And this relationship, called the Stokes-Einstein relationship, was proposed by Einstein, and this was a crucial factor which was used to basically by Perrin. He must have calculated the diffusion constant. And he didn't know KB and he didn't know R as well. So he would need to have an independent relation, or he could take two different size particles somehow. If he could figure out what size of particles he was using, if he exactly knew, then he would be able to figure out KBT. I don't exactly know the details of Perrin's experiment, but let's quickly see. This is not the rigorous derivation of how one can make sense of Stokes-Einstein's relationship. And for that, what we shall consider is, suppose you have a tube and you have suppose a glass jar and you have gas molecule, not gas molecules, Brownian particles suspended in the fluid, and you have a force due to gravity acting. The origin, x equal to 0 is this plane. You see there's a density variation, Brownian particle in equilibrium under gravity, right? And there's a potential acting minus Gx. Now you see there is a concentration gradient. Now, because there is a gravity, right? Uh, as you go up, there is a gain in potential energy. The energy of the particle increases, right? And you might know from your Boltzmann statistics, the higher the energy, lower the probability that the system will be in that micro state, will have those positions. I don't know. I mean, if you have done your statistical physics, you will know what a micro state is. Position and velocity defines a micro state, at least for classical particles. Quantum particles, you have to tell the energy level. But these particles are in micro states of higher energy, because kinetic energy remains the same due to KBT, but they have higher potential energy, right? But there is a concentration gradient, and if there's a concentration gradient, then due to Brownian motion, these particles would like to go from a region of high concentration to a region of low concentration. But you know that in a gravity, and if you're Brownian particles, such a concentration gradient is maintained. In fact, Perrin also used this, if I remember correctly. I don't remember. So the gravity creates a concentration gradient, right? Because of Boltzmann statistics. On the other hand, because of the concentration gradient, there should be a drift of particles due to Brownian motion from a region of high concentration to low concentration. When these two currents are balanced, you will reach equilibrium, right? So let's use this. So in equilibrium, the current due to diffusion and concentration gradient is balanced by the particle current by force field due to gravity, Boltzmann. So in terms of, since there's a force acting, on each of the particle would like to go down, and then the force acting on each particle is zeta into Vd. Vd is the drift velocity. If there's a force, it's moving in a certain direction, the force is acting, the frictional force is zeta Vd, right? And if there's a large number of, on an average, there's a drift velocity. Some are moving up, some are moving down. So here you are really calculating the net number of particles which are moving down, the current, number of particles moving up, number of particles moving down minus number of particles moving up into Vd is the drift current, the net number of particles is coming down due to gravity, right? And so this Vt you can replace by F by zeta, right? Now, the particle density, because of Boltzmann statistics, this is the density at x equal to 0. It is decreasing. It's like n0 e to the power minus mgx is fx by kbt, right? Uh, yeah, remember x is in the negative direction and so on. F is acting in the in this direction and x, yeah. So remember the origin and so on and so forth. dnx dx, gradient of c. Remember the current due to diffusion is due to gradient of c. So I have taken the derivative. And if you multiply by d, you get the current. So you have essentially calculated the current due to concentration gradient. This is due to diffusion. And you can calculate Jx by n, right? Which you get as df by kbt. Now, if you equate, okay, this I'm doing a bit in a hurry, I'm a bit tired, but I'll tell you where to look this up. Now, equating these two currents, essentially, df by kbt and, J drift by n is f by zeta, you get your Stokes Einstein. But there are much better derivations as well, but this at least gives some intuitive idea. Now, this was basically, you can look it up again from page 30, section 1.3.3 of physical hydrodynamics. The authors are these four authors. These are fluid dynamics books essentially. The other stuff that I've told about is taken from the elements of non-equilibrium stat mech, V. Balakrishnan, and some of the random walk stuff or some of the derivations which I said, you can figure this out and this will be a Gaussian. Uh, that is taken from a polymer physics book called Rubinstein and Colby, section 2.5. So you can have references of all of this. The last question, what you should think about, actually, I have a small discussion on the next page, but I'm too tired, is why are random walks? What are random walks? As I said, the random walk derivation I took from a polymer physics book. What is random walk doing in a polymer physics book? Polymers is something which you don't really associate um, a random walk with, right? Actually, you do, because what you have come across till now is polymer chemistry. But if you're doing polymer physics, and where we basically, so we don't, we basically, the polymer physicist doesn't really look at the chemistry. He glosses over it. He's looking at statistical properties, entropic properties. Why entropic? That will come in the part 2 when I talk about physics of life. I talk about chromosomes. This is the background stat mech. I need to discuss that. But a polymer physicist will say, okay, this is the so-called bead spring model of a polymer. That, okay, there's a long chain, but all the chemistry and carbon and nitrogen and I don't know, phenyl and benzene are essentially spheres. This is the so-called spherical curve model. And the polymer is essentially a large number of particles connected by springs, right? And all the details. So you're basically looking at the length scale much larger than each of these chemical constituents. And basically what you consider is, and this polymer can take large number of configurations, and more on that in the next class. But if there was at a certain instant of time, you had frozen a polymer, what you would say from one bead to the other, this this one bond from one bead to the other, this spring you could replace by a vector, and the second bond by another vector, the third bond by another vector, and fourth bond and fifth bond and sixth bond and seventh bond and so on and so forth. And what you see again are vectors. If this was a completely flexible polymer, and I mean, even if it's not, then on large length scales, you can approximate it by a flexible polymer beyond a certain length scale called the cool length, which I won't get into. But basically, thermal fluctuations will make even rigid polymers forget its ori original orientation. And you're really looking, the physicist really is looking at polymers at that length scale that is flexible. And then each of these bonds are randomly oriented with respect to each other. This bond and this bond, there's no correlation in the direction. And if you look at this conformation, this would remind you about a random walk in 3D space. So this is the so-called ideal random walk where chains can overlap, right? So two monomers can sit on top of each other. On the other hand, polymers are better described by the so-called self-avoiding random walk or SAW, about which I'm not going to discuss much or none at all. And if basically these bonds were basically sitting on a lattice, if it was an ideal random walk, then this bond could sit both here or go there. But if you have a self-avoiding random walk, if this bond was sitting here, then this monomer and this monomer would sit on top of each other. But in reality, two monomers which are made up of electrons and atoms and so on, they cannot sit on top of each other. Hence, it is self-avoiding random walk. So even if you do polymer physics, where physicists look at polymers as a quantity with a huge amount of entropy with a large number of configurations. These configurations correspond to large number of microstates. Large number of microstates correspond to large amount of entropy. So there, each of these objects have huge amount of entropy. And we'll discuss this more. But all that I want to say that we want to do is polymer physics that again starts with statistical physics and the description of random walks and then self-avoiding random walks and then random walks with interactions and so on and so forth. So this goes on. That's why again, you can refer to polymer physics books for random walks. Okay, I mean, I think I've told much more than I had planned to say, or rather I went rather slow because I thought there would be students from second year, third year, fourth year, I don't know. So I hope this was accessible, though a bit long. You can just break it up into smaller pieces. And with that, I will finish the statistical physics background, at least the gist of it. And I'll send you another lecture tomorrow, which is on the physics of life and my work and chromosomes and so on and so forth. With that, I will finish. I'll stop recording.